Then I can say hello officially. Happy Garbage Day.
Happy garbage day.
Happy Tuesday. Is it lovely outside?
It's not bad.
Yeah, it's like a lovely fall day, not too hot, not too cold. We've been talking about homework as we're waiting for folks to enter. Any other homework questions I can talk about? Zoomers, anything from the chat, or you can talk?
So I have a question about Owens D
Yes.
exercise, and that's under section 2.
Section 2.
To be very specific, it's question 21.
31. 30. So the last.
21,
Uh,
24, and 37.
Or the D. This is this one? 33.
Yeah, 21, 34, and 37.
Oh, down here, or
Computational 2.
okay.
Yeah,
Maybe I misheard you.
Number 24 also has D, and number 21 also has D.
Gotcha. Okay. Yep.
Yes.
31, yeah, 31, 34, and 37. Yeah.
Gotcha.
So it
Okay.
has to do with Owens D.
Yes.
That's affects that. I'm not able to figure it out. How to take out the Owens D. I'm sorry.
Okay. Let me show you where to look, because this is something that you have to compute separately. It's not given by default.
Okay.
And by compute, I mean make your software do it, not like you doing it with the calculator, although that probably will work in this case. There is code, so it's based on, this homework that you're working on right now is based on example 3. And in that example, on page,
Yes.
what page is this? 5. So there is, if you're using Stata, then you can use this right here. Copy that line verbatim. You don't have to change anything, because it's going to access the saved results for this lincom. So I would write a lincom for what slope you want the D for, and then just paste this and run it afterwards.
Got it.
What it's doing is accessing the saved results for the estimate and the standard error. So this part is T.
Okay.
And then this is the denominator degrees of freedom.
Got it. Thank you.
If you're using R, then I have some good news and I have some bad news. The good news is that you can copy that and get a D out of it. The bad news is that you have to change everywhere it says something about pred class or save pred class or model class to whatever your stuff is called. However, you're about to be very, very happy with me. In your new example over the weekend, so I asked my husband for help writing R functions, and he wrote one. And then I was like, oh, this is easier than I thought. So I wrote a whole bunch of functions to automate this stuff. I know, it's going to be amazing. So then you don't have to actually go through and find all the places to change, because that's what the function does. Yeah, it's going to be awesome. Erica's like, finally, she's learning something. Hey, I started using R for the first time 3 years ago, and I have slowly gotten better at it. But this is a major turning point. You're going to be very happy. So this will be the last time that you have to see like code that looks like this and change all the spots in it, because it's annoying. So, all right, does that help with the D? Okay, excellent. What else can I help with respect to homework that is due tomorrow? Anything? Okay, then I do have office hours tomorrow for last minute questions as well. And just to make sure we're all clear, you don't have to have answered every single question to submit. There was a few folks that had misconceptions about that. Like if you can't find 1D and you get stuck and it's 11:58 and you're like, I gotta turn this in, do it. Because all of the computational questions together are worth 8 points. And there are, how many of them?
A lot.
Oh, this isn't a lot. Oh, only 45. No.
0.2 each.
Oh, no. In some of my classes, we get past 100 in terms of Yeah, it's more complexity. So if you, like, point being, if you get stuck on one answer and you can't find it,
Point two is
just
not
turn it
bad.
in. Like, it's like point something out of, point off. So, and it will tell you what it is when you get your feedback, so you can always figure it out later. Let's see. Other thing I would need to remind folks is that Thursday we are losing our classroom, so we will be on Zoom only for that day. Let's see. Anything else I'm forgetting? Oh, one more thing. Your next thing to do after you turn in your homework, formative assessment, due next Monday, and the TAs are going to lead it. Yes, so you should be able to answer all of those questions right now. And then after that, you get a week off. So I have room for a few Mondays where there's nothing due, and one is coming up. I released homework 4 to the TAs this morning, and they're working on that. I hope to have that open by the end of the week. That way, if you want to work ahead, you can. It is going to be based on the second half of example 3. So the piecewise models and the ordinal slopes models. So you already know how to do everything for that as well. All right, I'm cold in here. Is the air conditioning really cold? Yeah,
That
I'm like,
jacket feels nice.
I'm shaking, which is unusual. I usually really run hot when I'm teaching. So if you hear my voice shaking, it's because I'm cold. I'm not actually terrified. In other situations, it might be the opposite, but no. This is my happy spot. All right, then we have some new stuff to talk about. But before we do new stuff, how about we do reviewing a little bit?
Yes.
I should assume you don't have perfect recall of every word and expression that's been used? I can assume that? Okay. So lecture 4 starts off with a little bit of review then.
I can ask, what is the full name of GSS?
General Social Survey.
General Social Survey. Oh.
Yes, it was a data set that was used in a STATA textbook that I used to teach from. And so I stole it a long time ago. It's from 2012, actually. So these are real data.
Thank you.
Yep.
General Social Survey.
Yeah. Yep. So, reviewing time. Fixed effects come in 2 kinds, right? Intercepts and slopes. Okay. So far we've talked about instances of general linear models predicting quantitative outcomes, what the role of each predictor variable is in creating a custom outcome. Use one or more fixed slopes. So if you have a variable that is quantitative and you're expecting a linear relationship only, that can be done in one slope. If you have a binary predictor, 0s and 1s are the only possibilities, there's only one difference between the two, that takes a single slope. In other situations, to fully characterize the relationship between a predictor X in predicting an outcome Y, you need more than one slope. So for instance, if you have a nonlinear effect, so like an age curve like we had in the last example, then you can capture that with x and x squared as predictors. If you have an x that's going to be split into pieces, like we did for education, then piecewise splines, we might take 2 or 3 of those. It's also the case that if you have a categorical predictor with more than 2 categories, that takes more than one slope. So the rule is capital C stands for the total number of categories, minus 1 is what you need in terms of slopes. So it's C categories, C fixed effects in total, because the minus 1 is for the intercept you already have. So if I have 4 groups, like in your current homework, then it takes 1 intercept and 3 slopes to differentiate those 4 groups. Here is the formula, by the way, that you can compute this. And only some of the differences are given by your slopes. The others are all linear combinations that you can get by subtracting them or adding them or however it works out in your instance. So in each of these cases, what we want to know about the slope from an unstandardized solution, meaning keeping the units of the variables in place, is the estimate. That's its most likely value given your data. That is formed as the number that minimizes the ease across your sample. So what's called the objective function, the thing that it is trying to get to as the best answer, that is minimizing the sum of the squares residuals. We also need the standard error. What's that? And you're going to answer this question about 7 more times too. By the end of the semester, you will know this. What's a slope standard error tell us? I'll take gestures, words.
Deviation of your population.
Deviation from a population. How far off, on average, your sample slope is from the population slope. Conceptually, it's inconsistency, or wiggliness is the word that I tend to use. How wiggly would your slope estimate be across repeated samples of the same kind? Estimate divided by standard error gets you to your t. That's your test statistic. That's a distribution that essentially standardizes your slope so that we can figure out where unexpected territory starts. That is given by alpha, type 1 error rates. How often are you willing to be wrong if the null hypothesis is true? Then a corresponding p-value shows up on your output that tells you where on t your result lies. What is the probability that you would find a slope that big or bigger if the null hypothesis were true? And usually it's a null of 0. So then we have degrees of freedom, 1 if you have one slope, more than 1 if you have more than one slope. Denominator degrees of freedom, what's n again?
Population.
Other one.
Sample.
Sample size, yes. Number of people, usually. What's k? Number of fixed effects, including the intercept. So we always have a fixed intercept in our models. So when you have the formula for variance, it's just n minus 1, that's why. Now it's n minus k because it takes more stuff before we can compute variance left over. More stuff, more slopes. And we can get effect sizes by converting the t into a partial r. We're going to talk more about what that means today. Or I'm labeling this as partial d because it's the same kind, but no one calls it that. It's Cohen's d, after the person who made it. But in terms of the category of effect size, it's a partial. You'll get to hear the other version today, which is semi-partial. You heard of that one before? Part and partial, or semi-partial. Yeah, fun new vocabulary. So if I have x1 as my predictor, all by itself in here, beta 0, that's my intercept. Intercept is always the expected y when your predictor is 0. Beta 1 is my slope. That's the change in y for a 1 unit change in x, or as I have written here, difference, because people aren't changing into each other. If all I have in the model is x1 predicting y, I would call this a bivariate relationship, meaning just 2. If I standardize this slope, it becomes the Pearson correlation between these two variables. So this is an instance in which a model really wouldn't be necessary. I could answer the same question as to how x1 relates to y by computing a Pearson correlation and looking at that p-value, and that p-value will exactly match the p-value from my slope. E then is what's left. How wrong are you? So everybody who has the same x1 as someone else will get the same predicted y, but their e's will differ, because e is how far off your prediction is from what your y actually is. If I had a second predictor in a separate model, everything would follow the same way, except that now we're talking about the relationship of x2 instead. In terms of general hypothesis test, when you have more than one slope, besides just looking at what happened with each slope, we also want to pay attention to how well they work together to capture information in y. So that gets us to a different test statistic known as F. So F looks like this. You have to know how many slopes are in your model. That's degrees of freedom numerator. How many more slopes you could possibly add. That's degrees of freedom denominator. The numerator part then here is how much information did your model capture divided by how many slopes it took to capture it. The denominator is how much information is left over divided by how many slopes you could have still added. Another way of writing that is as a function of r squared. So essentially what F boils down to is it's a ratio of how much you know versus how much you don't know. F has to be positive because these are in squared units. So SS stands for sums of squares. So it's a significance test that goes with the r squared. and it is evaluated per slope. So that means that you could have a model with 10 slopes in it and have one slope be really, really useful and the others 9 don't help you, then F would probably be non-significant because it's per slope, and the bad ones would drag down the average. R² then is computed this way. So it's computed this way to ensure it stays positive by using sums of squares. It is the square of the correlation between y and y hat. You can also think of it as the proportion reduction in the variance relative to an empty model. What's the highest R² can be? 1. What does that mean? 100%. Variance explained. E has left the building. That's what that would mean. Everything is perfect. What's an R² of 0 mean? No explain. What kind of model would generate an R² of 0? Empty model, yeah. Nothing in it. Nothing to explain. There is another version of R² that you will see on your output, just to remind you. I don't use this one, but in case someone wants you to, it's the adjusted version. It takes your original R² and corrects it for sample size. This is more of an issue in smaller samples. It's easier to get a higher R² when you have a very small sample. This, by the way, also lends itself to how R² is computed in more complex models, such as multi-level models in my earlier class. So if we only have one fixed slope, I don't need to do any of this. If the model is one slope, then the t for that slope squared is the model F. The R correlation that would describe the effect size for that one slope squared is R². There's a 1-to-1 correspondence between model and slope if there's only one slope. Moving on then. We've talked about multiple slopes at the same time, but they were all for the same predictor. Like we had age and H², or we had the 3 pieces of education, or we had the 3 contrasts to differentiate the 4 golf groups, that kind of thing. So in that example, they work together to describe really one idea, like does age predict income? Does education predict income? What we're headed to now, as you probably would have guessed, multiple slopes for multiple kinds of variables at the same time, because this is the world that we typically live in. Most research questions are phrased in some way to say something like, after controlling for X, what is the relationship of Z and Y? Because there's always stuff you have to control for that's already known to affect your outcome in the literature. Question? No, scratching, okay. So rather than having what I call bivariate relationships, meaning between 2 variables at a time, now we're getting into unique relationships as the new word. Meaning after controlling for the other predictor contributions in the model, what does your predictor bring to the table uniquely? So terminology changes, complexity increases, and we also now have different ways of thinking about effect size. And there's not going to be one right answer per se, but they tell you different things. So I want you to understand those distinctions. Now, because this can get fairly abstract, I wanted to go with the concrete idea to start with. This is the cast of a television show that was on for several years. It ended a couple years ago. It was called This Is Us. Any other fans of this show in the house today? Couple of us? Zoomers? Anybody? Oh, 2 hands. Big fans. The good news is that you don't need to have watched the show to understand my example, okay? I just wanted to come up with a family to be concrete. And I like the show a lot, and so I built this example when it was still on. So for those of you who are unfamiliar, this is the cast. But the mom, who is Mandy Moore right here, is actually younger than her children. So what happens is that this cast goes forward and backward in time. And so you see, like, this is what she looked like when the kids were little. Then she puts on, like, an old lady suit to look older in the scenes where she is their mother and they're this age. This is the dad, same thing. So this is what he looks like. He had a nice, sort of 70s look going on in these scenes. And they had, Rebecca had given birth to triplets in the hospital, and one of the babies died. And at the same time, Randall was dropped off at a fire station by his father, and he was in the hospital that day. And so just as a happenstance, they were like, we were meant to have 3, here's this baby who needs a home, so they adopted him. So this is the cast. So this is Randall, this is Jack, Rebecca, Kate, and Kevin. So I'm using them as an example to talk about cleaning a house as a concrete representation of explaining variance. Okay, you with me? So here's the story. So let's say that Rebecca has had it with 3 messy teenagers, and she decides to design an incentive to get their house clean. So let's say their house has 10 cleanable rooms in total. They each have a bedroom, 2 bathrooms, living area, kitchen, dining, garage. Okay. So she makes a deal with them. This is a very sweet deal. For each person who cleans at least 1 room by yourself, you get a new Nintendo game. Hooray. So that's an individual level prize. But she also wants the whole house to get clean. So she decides to make an incentive. If at least 8 rooms are clean, the family gets a new TV to play their Nintendo games on. As 8 would average 2 rooms per person. So this is the deal that she sets up with them. She decides to let them figure out who's going to clean what, and she goes out shopping, and she comes back later. So let's say she comes home, and here are the results of what happened. So we have Jack claims that he cleaned their master bedroom. Kevin claims he cleaned his bedroom. Kate cleaned hers. Randall, of course, in the story is an overachiever. So of course Randall's going to Randall and do everything. That's his personality. But Kevin and Kate also claimed that they helped with the living room. Odds are good that Randall did most of the work, but that's fine. Jack claims that he cleaned the kitchen too, and so did Randall, and Jack and Randall both claimed that they cleaned the dining area. Well, the good news is that 9 out of 10 rooms got cleaned. No one went out to the garage, so the family gets a new TV. Whoop, whoop. But how do we judge individual effort? Because she wasn't here. She doesn't know who actually cleaned the rooms. This is just what they told her. Well, we know that Jack, Kevin, and Kate each cleaned 1 room that no one else said they did. So they each get 1 game. We know that Randall cleaned 3 rooms that no one else said they did, so he gets 3 games. But no one fairly can get credit for the living room, the kitchen, or the dining room because we aren't sure who the credit should go to. So, from cleaning to modeling, if you can take care of those ideas in your head in approaching this, another way of looking at this problem is what's known as a Venn diagram, or there's another name for it that I can't remember off the top of my head. Let's say that Y, your outcome variable, is the house. The question is, how much of the house got clean? How much of Y got explained? So we have 1 person here who is X2, 1 person here who is X1, because I didn't have room to put 4 circles on the slide. So if we divvy up the proportion of the house that each person cleans, the proportion of the variance that each predictor explained, then area A is what X1 did that X2 did not. So that's like 1 room that they cleaned all by themselves. B is what X2 did that X1 did not. So that's like B is the room that they cleaned that no one else did. C is the common areas that multiple people claimed they cleaned, so we don't know who to give the credit for. And then E, skipping over D because E makes more sense here, is what's left. Like this would be the garage that no one touched. Okay, with me so far? All right. So then we have a couple questions to answer. One is about the general utility of the model. How well did the family work together to clean the house? How well do the slopes work together to explain variance? The way that we answer that is the same way we've already done, the test of the model R-square. So R-square tells us the proportion of the house that got cleaned. It's also the square of the correlation between the actual outcome and what is predicted by the model. And we have an F-test that goes with it to say whether or not that R-square is significantly greater than 0. That part hasn't changed. The part that's new is that R-square takes into account the common part. Because R-square is what proportion of the house got cleaned. It is irrelevant from that perspective who gets credit for area C, because area C is cleaned. We're just tracking how much is cleaned. But for the purpose of awarding individual prizes, C shouldn't count. So specific utility then is about the unique contribution of each predictor to the model or each person in helping clean the house. and nobody gets credit for what's in common. So the p-value and the slope estimate that's going to go with these are reflecting only uniquely what that new predictor brings to the table that none of the other predictors already covered. That's the new idea. We didn't have to worry about that before, but now we do. So taking that into account then, we have to change how we talk about our slopes a little bit. We do. So if I put x1 and x2 in the model at the same time here, how many fixed effects do I have? 3. How many slopes? 2. So now, rather than these being parts of the same variable, these are different variables conceptually. They're different things. But the same rules apply. The intercept is the expected y when x is 0. Well, now there's 2 x's. So this is specific to the 0 value for x1 and the 0 value for x2. The slope of x1 is still the relationship between x1 and y, but now it is the unique part of that relationship specifically. So there are a lot of different phrases people will use to talk about this. I like the word unique because it's the most parsimonious and I think easiest to follow. People will also say that the slope of x1, beta 1 is controlling for x2 or adjusted for x2, holding constant x2, partialing out x2. All of those things mean the same thing. Your textbook has a very nice description of this. I would encourage you to read that section if this is something that is not intuitive necessarily. They talk about it in terms of like predicting one variable from another and then putting the residuals in the model, and that's what the slope is for. The point of the story then is that each of these slopes is only going to capture the unique relationship of that variable, discounting whatever is redundant with the other predictors. At this step, though, beta 1 is still assumed to be constant over all values of x2. So it's controlling for, but it's not specific to. That's a distinction that we'll get in the next unit. The other slope is interpreted in parallel. So beta 2 captures the relationship between x2 and y that x1 didn't already capture. Neither of them gets credit for what is in common. And we would call this an additive model because these things are just adding in together into one function rather than multiplying each other, which would be an interactive model or over additive or under additive model, which is what we're doing next.
Oh boy.
Oh boy. Yeah, that's one of my favorites. I love interaction terms. A lot of hypotheses go with interaction terms, but not today. Okay. So trying to help translate then how the numbers rearrange themselves, this is how you can actually solve for these terms using just the mean, standard deviation, and correlation between two variables. So like you can solve for beta 0 with this, you can find beta 1 with this or this. You can go back and forth across standardize. For a 2 predictor model, it's similar in structure, but note the part that is in common is subtracted off here. So the standardized slope is the relationship between the predictor and the outcome, but then correcting for the part that's in common, which is what's in parentheses here. And then it's done in parallel for the other one as well. So I have this a couple different ways because one way may make more sense to you. So I would say that the old way of thinking about R square is the same. It's still accurate. I can also think of it this way, proportion of the total variance that's explained. The new way of doing it is taking into account the common part. So I found a couple different formulas. I thought I'd throw these in here. If this makes sense to you, great. If it doesn't, then just hang on to the bold part. R square counts the common part. That's the take-home message. Individual slopes do not. So R square is like how much of the house got clean. I don't care who did it. Individual slopes is which room did you clean, and that goes with your inference in the model. The standard errors also have to take into account what is unique, and so that formula changes as well. So the initial formula I showed you for how standard errors are found is the residual variance of the outcome divided by the variance of the predictor that the slope is for, multiplied by sample size minus k. Remember fixed effects here. That is all still true, but now there's this new part in here. 1 minus the unique variance in x. So the standard error reflects, in part, how much information the predictor uniquely brings to the table. And if it doesn't bring a lot of information, then standard errors go crazy. They can get very large. So all things being equal, a standard error for a slope, its expected inconsistency across samples, is smaller when there's less variance left over. So if you've done a better job explaining the y variance, you have a smaller standard error. Practically speaking, what that translates to is that order can matter in terms of drawing conclusions. Like if I put a predictor in a model, I look to see if it's related to the outcome. I say, nope, it's not significant. I'm going to take it out, go put in something else. If I were to revisit that predictor down the road after adding more things that explain more variance, its effect could become significant at that point because there's less leftover variance in y. So order can matter from that perspective. It is also the case that the standard error will be smaller to the extent that the predictor is less related to the other predictors. Ideally, the best situation is that you have uncorrelated predictors, because then their standard errors are going to be as small as possible. So why do we care? If the standard error is smaller, that means the test statistic is bigger, which means your p-value is smaller. You have a higher chance of detecting something, higher chance of calling something significant, higher power. So recommended strategies then. Step 0, make your variables. That part hasn't changed. So if it's a quantitative predictor, make sure that 0 is meaningful. You may need to subtract or add a constant so that that is the case. If you have a categorical predictor, you will need to make multiple binary versions of it so that you can put those binary versions in the model, that you've been doing that already. I then think it's useful to examine the bivariate relationship of each predictor to be included. So 0 order is a synonym for that, by the way. So we can do this fairly straightforwardly. If we have quantitative predictors, those can be thrown in a Pearson correlation matrix. If you have a variable that takes more than one slope, though, then that requires its own model. So like if you want to talk about a 3-category variable, you can't estimate a Pearson correlation with the dummy codes because they are treated as separate things. It won't understand that you intend it to mean just that group versus that group. Models make the slopes work together. Individual correlations do not. So if I have like a 4-category outcome, the right way to examine the relationship bivariately with just that outcome and that predictor, predictor, not outcome, is a regression, because then the R-square tells me about how strong that relationship is captured by the 3 slopes. I would then look at the relationships among the predictors. If you have predictors that are very highly related, they are going to fight against each other. And you probably won't be able to use both of them because they'll kind of knock each other out in terms of what they each bring to the table uniquely. And you can quantify shared variance among your predictors using these same steps. Step 3 is to combine your predictors into one model in a way that corresponds to your research questions. So this is very much contextually driven at this point. The order is up to you. So for instance, if I had a question that says, how does y relate to these 3 things? And I don't have a priority system or anything with respect to those, I would throw them all in the same model, report the model F for the R-square, and I would talk about the direction, the significance, and the effect size of each predictor. And we'll talk more about your options for doing that in just a second. If I had a more sequential kind of question, like after controlling for x1, how does x2 predict y? Then, after controlling for x1 and x2, how does x3 predict y? I would then do it in a series of steps. I would put x1 into a model and talk about its direction, significance, and effect size. Then I would add x2, talk about the f for the model, the change in the model, so the R-square change, this is something that we're going to get into, and well as what happened to the new predictor. And then I would also comment on how the effect of the first one changed after adjusting for the second. And I would do the same thing again after adding in x3. So it's going to be up to you whether it makes sense to think of these as just like 3 variables that are all sort of on equal footing versus some kind of sequential driven hypothesis test like this. I can't tell you what the right answer is, but these are the most common ways that people would approach the problem. I think that a stepwise strategy is useful if there's a clear hierarchy, but otherwise a simultaneous strategy is more defensible. And by the way, I'm not going to get into any of the automated routines. Did you know that like AI will do this for you before there was even AI? Like back in the 1970s and 80s, they came up with routines for stepwise regression, forward elimination, backwards elimination, where you just say, hey, here's my variables. Can you figure out what my model should look like? And it'll do it for you. Now that's lovely if your only goal is to capture variance in your outcome and you don't care how that happens. It is less ideal if you're trying to make theoretical statements about how these things relate to each other. Then the computer probably shouldn't be in charge of that. But that is a thing that you can find in software. At this point, some folks would tell you about multicollinearity, which by the way is spelled a bunch of different ways and sometimes has multi in front of it and sometimes doesn't. This is not a thing you need to worry about in your lives, okay? Just don't. It's not a big deal. It used to be the case that when computers were less good, I would say, that having very high collinearity could cause estimation issues, but that's not really a thing anymore. So you may see these statistics printed or talked about on output. Tolerance or variance inflation factor, which these are two related to each other. These are indices as to how related your predictors are, but you should already know that from examining that in the first place. The bottom line is that the more your predictors have in common, the harder it's going to be to figure out what they each bring to the table uniquely. That's it. There's nothing you can do to fix that. It is that way. So it's something to keep in mind, but it's not something that you can necessarily fix. Only when you have something called singularity is that a problem. So if you see like an output message that has the word singular, that's bad. You wouldn't think it sounds bad, right? Like it's not bad to be a singular. What it means is that your variables are redundant. So where that can happen, I've had people ask me if they can do this before, for instance. If I have a test that has two subscales and I want to put those subscales into the model as two predictors, it's fine. If you try to add the total score of those two subscales in as a third predictor, it will break because it's perfectly redundant. It can't come up with a third slope for something it's already covered the slopes for. If you accidentally made 4 dummy codes for your 4 groups and tried to put all 4 in the model with an intercept, this would happen as well because the 4th is redundant. And so you will know that this happened when on your output next to a predictor there will be just emptiness. Like there'll be dots or just empty space. It's like, so that's a real problem, but that's on the side of the user, not the side of the math. So when would this be an issue? I think that it could happen in a lot of real world situations. So for instance, if you are in a medical setting and you have some way of testing for a disease that's very invasive and expensive, and someone comes up with the quicker, faster version, a reasonable question would be like, can I use one predictor to replace the other? A real-world example of this, colonoscopies. Fun things about aging. But you know what? There's an alternative. You can send a specimen in a box to be tested, and if that specimen is fine, you don't have to have your colonoscopy. So that would be a question of like, can I use one measure to replace another? If you have those kinds of questions, then I would approach this differently. You would want to compare what's known as non-nested models. So for instance, if I have a model that has predictors A and B versus a model that has predictors A and C, then you can't test directly the change from one to the other because they're not a subset of each other. But there is a way to do it. So here's one breadcrumb. Hotelling's T is a way that I learned how to do it back in the day. There's also something called dominance analysis, and this is discussed in your textbook. So there are ways to answer questions about how exchangeable predictors are. It just depends on whether it's part of a nested model comparison or not. So, how are we doing so far, folks?
Lots of stuff.
Lots of stuff, yeah. Do you want to talk about effect size? Sure. You're like, is that rhetorical? Yeah, it was sort of rhetorical. As you might imagine, there's a lot of different ways to characterize how much uniqueness there is. And so I want to give you some choices and then I'll give you some recommendations. So why do we need effect sizes in the first place? Because slopes are in units. I can tell you whether a slope is significant or not, but I can't really give you a sense as to how large the effect is if it's in units I'm unfamiliar with. So effect size is a way of standardizing slopes into something that I can look at it and go, oh, that's 0.8, I know what that means. Like a correlation of 0.8 is a strong relationship. A correlation of 0.1 is a weak relationship. So there are multiple ways to do this. Could be relevant per fixed slope. So I might want to know an effect size for every single slope in my model. I also might want to know the overall effect size for a set of slopes that work together for one conceptual predictor. So like the 3 slopes that differentiate 4 groups, I might want an effect size for that as a unit. Effect sizes are useful not only for your reader, but for future people. So people who do meta-analyses. Is this a term you've heard before? A study of studies, essentially. What those seek to do is combine effect sizes across similar studies to try to figure out like what the average effect would be and how that effect might differ as a function of study characteristics. It's also useful for people who are trying to do research on your topic to be able to anticipate how many people they need to plan their statistical power. You need an effect size to be able to do that because power is always specific to a given effect size. So there are choices in an R metric, including standardized slopes. I'll talk about that in the next slide. There's also what is known as semi-partial correlations or partial correlations. Do those sound like they would be synonyms? They kind of sound the same, don't they? They're not. And just to make it even more fun, because statisticians are mean, as we discussed last week, we're not going to call these R's, we're going to call these etas, a new Greek letter. For no damn reason, as near as I can tell. We just changed the way we talk about it. Job security, I guess. And in the same way that we had regular flavor R square and then there was an adjusted version that corrected for smaller samples, we have an adjusted version of these too, and that's called omega, which is this W looking thing.
Is this also Greek?
Yes.
That's all.
Yeah, I know most of the Greek letters at this point, not all of them though. But I will tell you that when I choose notation in my teaching, I only pick the ones that I know and can reliably draw on a chalkboard with a marker. Like there's 2 that I still don't know because I named them squiggle 1 and squiggle 2 a long time ago. And I'm like, that's when I look at it, it's like, oh, that's squiggle 1. I never use those because I can't draw them. Erica's not laughing at me. What are they actually called? Do you know? Yeah. At the end of the day, these are representations, right? And so as long as you have a way to represent something that's concrete, I think that's sufficient. But I just want to point this out to you, make you aware of this, because I'm going to talk about these as R's because that's what they are. But you will see the word eta or this notation show up an output for reasons. And if that weren't enough, there's also squared versions. So you can have an R version or an R squared version, and that can be partial or semi-partial, and then you can have the omega version instead. Oh, and then there's one more. There's an F, but it's lowercase this time, which makes it not the same as the other F. I know. So first off, standardized slopes. That is what I was taught to look at back in the day. I think that is still what most people look at for FX sizes because it shows up very easily on your output. So in SAS, you can get that by switching from GLM to reg as an option. Stata, regress, comma, and the word beta in lowercase gives you the standardized slopes as the last column of your output. And R has a little function called lm.beta where you can feed in your model and it will print out the standardized slopes. And I believe you did this in homework too. Does that sound familiar? Maybe? Maybe. Yeah, I don't remember what I had for lunch today. You're probably feeling similarly at this point in the semester, but you did this in homework too. Okay, previous you did this. They're also used very commonly in path models, but here's why I don't like them. And I'm not alone. This person doesn't like them either. I found this blog post that railed against these things, and I thought it was a very useful blog post, so I'm citing it here. Thank you. Number one, they're not actually in a correlation metric. Standardized slopes do not range from -1 to +1. They range from infinity. They do. Because the standard deviation of x is what's used to standardize them, but the standard deviation of x is no longer relevant in most cases. What this effect is about is the unique part of x that none of the other predictors are contributing. The room that this person cleaned all by themselves that no one else cleaned. So what happens then is that we're standardizing with the wrong number. And it turns out, by the way, if you take the standardized slope and you multiply it by the unique standard deviation of x to try to put it back into the right metric, that's what semi-partial r is. So that is actually better, and that's where the person who wrote the blog post lands as well. The other reason you don't like it is when we're dealing with interaction terms or quadratic terms. So an interaction term, as you'll see in the next unit, is when you take two predictor columns and you literally multiply them together to create a new third column. That is used to address questions of moderation, like does the effect of this predictor depend on where you are on this other one? Those kinds of questions. But it turns out that order of operations matters. You end up with a different result if you square and then, or multiply and then standardize, versus if you standardize and then multiply. Those aren't the same thing. And it's ambiguous as to which should be done. Also, as noted in your textbook, if you have differences in sample size across categories of a categorical variable, then that renders different standardizations as well. So for these reasons, I don't like them. They also don't scale up into other models that I teach. So my spring course on generalized models does not use these. Neither does multi-level or mixed effects models, which are the other courses that I teach as well. So what to do instead? Back to Venn diagrams. First off, the semi-partial family. Semi-partial and I are good, like these guys. They're also known as part, though, by the way. That's a synonym. These two words mean the same thing. This tells you, in the squared metric, semi-partial eta squared, or SR squared for simplicity, how much of the variance that predictor explained. Boom. I like that interpretation. It's very straightforward. So it's computed in terms of sums of squares. In terms of the area, it's how much did that predictor do uniquely that none of the other predictors did, divided by how much variance is there in Y in total. All the areas put back together again. The amount of the R square that predictor is responsible for, boom. I like semi-partial eta squares. The good news is that they will not be influenced by adding extra predictors to the model, because the denominator is all the variance in Y. So it doesn't matter to this statistic how much of it is explained or not. Unexplained plus explained is down here in the denominator, all of it. By the way, you can get this from the t-test statistic. So I have code functions in R that I wrote to do this. So it's a function of R squared and denominator degrees of freedom as usual. And there is no analog to Cohen's D for this, by the way, because D implies that group is already in the model, so there's no taking group out of the denominator here. So I like this one. I like this one less. This is partial eta and eta squared. So this one ignores what the other predictors did. It's only focused on the contribution of this predictor relative to the residual variance. So areas B and C are not part of the story. So this is how much of the R square that would be left over that's eligible did this predictor get. So this means partial eta squared is going to be influenced by what else is in your model. And that means they're not comparable across different studies that use different models with different stuff in them. Here's how you compute it. So because I think this is potentially confusing with respect to R squared, I don't usually deal with squared versions of this. I only deal with the unsquared version, because this gives you an effect size of how much action essentially your predictor had uniquely. And this is where you've done this in your homework. You'll do it again in the next homework. And Cohen's D is a member of this family. So I'm labeling it as like partial D to make that point, but no one calls it that. It's just Cohen's D. So summarizing then, semi-partial is how did you do out of everything possible. Partial is how did you do out of you versus what's left over only. So the difference is in the denominator here. And then there's a third one, Cohen's F, because he didn't have to just make a D, he made other stuff too. I think he probably made all the letters at some point be something. And this is F squared, which is computed this way, and I have no idea how to talk about this. This one makes 0 sense to me.
Looks like just a ratio.
It's just a ratio, but this is what people use in power analysis all the time.
Interesting.
I don't really know why. I'm sure there is a reason, but it doesn't make any sense to me. So let me give you a more concrete example that differentiates these things. Randall over garage. You know what? That wins. Yeah, this is how much did Randall contribute relative to the garage that he didn't do? That is what it would mean, and I still don't know what to say about that. I love that. All right, so let me talk about the Pearsons again here. So just to recall, Randall cleaned 4 rooms, Kevin cleaned 1, and they each cleaned 2 in common. So here's the scorecard here. So A would be 4, because Randall is the X1 here. B would be 1, because that's what Kevin is. C is 2 rooms in common, and then the residual would be 3 rooms. So how do we talk about what proportion of the house got cleaned? Well, if we talk about it in terms of semi-partial, then how much did Randall do? He did 40%, because he did 4 out of the 10 rooms that were possible. Okay, that's directly intuitive. Like overall, 9 out of 10 rooms in the house got clean. He did 4 of them. That's semi-partial eta squared. How much of the R squared did that predictor do? So partial eta squared, though, drops out the contribution of Kevin and the common part, and it's only how much did Randall do that no one else did. So Randall cleaned 40% of the house, but he also cleaned 57% of the house that Kevin didn't. That's harder to hang on to, I think. And Kevin, meanwhile, cleaned 1 room. That's 10%. That's semi-partial eta squared. But he cleaned 25% of the house that Randall left for him. There is an example in your textbook, let me back up here, that I liked with this about sharing food. So picture this, someone makes like a pie for an event, and the people at the event eat half of the pie. And so then you come home and you give your kids the rest of the pie. So let's say you start with the oldest person in the house, and they decide to take half of it. And then the next person in line is like, hey, you took half the pie. And they're like, no, I didn't. I only took a quarter. Who's right? They did take a quarter of the pie, but it was half of what's left. So did the first sibling take half, or did they take a quarter? If you said they took a quarter, that's semi-partial eta squared. If you said they took half, that's partial eta squared. I don't think the latter, the partial eta squared, is useful. I think knowing out of the original total is more useful. That is my personal opinion. You are allowed to form your own. So where I land is a combination approach. If you want to talk about variance explained, I think it is much more intuitive to do it as a semi-partial eta squared. How much of the R square is that predictor responsible for? Done. When it comes to individual slopes, though, partial R can be useful, because then it's like the unique contribution of that slope after controlling for everything else, which is what the p-value is already telling you. So there's a nice like symmetry there. The p-value is testing the unique contribution. The partial R is effect sizing that unique contribution. Can I make up that effect sizing? I just did. That's a new verb. So here's some examples from data set that you're already familiar with. And I promise this is the last set of examples with this. We're going to get new data soon. So you're probably tired of talking about income. So if I have an empty model, R square is 0, right? We agreed on that? And if R square is 0, so is semi-partial R and partial R. When we had education in the model as a linear slope, the R square for that was this number right here. When we had binary marital status in the model as one linear slope, because there's only one difference between the 0 and the 1 group, this was the R square. So if you were to naively think about what would happen if I put them together, well, this is how much education is related to income. This is how much marital status is related. The sum of these should be the expected R square, right?
Naively.
Yeah, naively. But no, because these two variables have some overlap. And so if we summed their separate R squares, that would be like double counting. And we're not allowed to do that. So it works out in the example I'm going to show you that when we put these two things together, their joint R square is only 0.1903 rather than 0.1986 you would expect, because these are a little bit related to each other. Education then has a semi-partial eta square of this much and a partial eta square of that much. So I can put this into context. I can say that education explained about 14% of the variance in income, but it explained 15% of what was left over after marital status had its say. Likewise, marital status has a smaller effect size, but it's always higher if it's partial than semi-partial. I think that's part of the reason why people report the partial ones, because they're higher. They look better. But that has to be that way. So this works out just fine because each of these predictors is described adequately with one slope. Like if I assume there's a linear slope for education, all I need is beta 1 to talk about it. If I assume that there's only one possible difference between these two groups, which there is, I only need beta 2. But what happens when you have something like this? This is the second model in the example I'm going to show you. This is putting together the two slopes that differentiate the three categories of our working class variable. It was lower, middle, and upper. Two slopes that describe how age relates to income, because it's age and age squared that we needed in separate models so far. And then education, we used 3 piecewise slopes. So each of these we looked at in separate models. Those are the R squares for that model. Here's the sum. When we put them together, the R square ends up being less by about 10% because these things have stuff in common. So education and working class in particular tend to be correlated. So I have the values here for all of this stuff and how that shakes out. So this is the part that I wrote a bunch of functions for, is how to generate these effect sizes when you have these combinations, because it's not useful to talk about each of these slopes separately necessarily. So here's why it's not useful. By the way, this analysis, we might call it ANCOVA. We might call it regression. ANCOVA means analysis of covariance. That refers to having grouping variables in the model as predictors and having quantitative variables in the model as predictors too. So effect size per slope, if I want to talk about the contribution to R square, or the R square that was possible after considering the other slopes, is problematic in most of these cases. So the working class predictors, these are set up so that low versus medium, or lower versus middle is the first contrast, and then lower versus upper is the second. These are going to be related because they're both related to low. So that means that we can't just add up, essentially, the effect sizes for beta 1 and beta 2 because they have some redundancy to them. So we can't compute semi-partial eta square from just adding up the semi-partial eta squares for each of these. We have to request it separately so that the joint part is subtracted out. Likewise, for age and age squared, this beta 3, cough, cough, homework question. This is the age slope conditional on what? Beta 3, the linear slope of age in this equation. This is the linear slope conditional on what? The centering point, yes. At age 18 specifically. So that means that any effect size is specific to that slope at 18. And the effect size would be different if the linear slope were centered at 20 or 25 or 30 or any other spot. And that kind of makes me nervous to think that I can manipulate the effect size by changing my centering. That feels a little cheaty to me. And education works the same way, even though they're not relative to the same reference point, because there's going to be overlap in these predictors, we can't add up their semi-partial eta squares together. So we'll have to do a little bit of extra work to get all that stuff. So the good news is that software has ways around this. So I'm listing all the different packages that we're going to see. The easiest one is SAS. Sorry, no one wants to learn that anymore. But you add one word, effect size, and all this stuff pops out for everything. It's glorious. Contrast is a statement that you can use that can do both generating f-tests for sets of slopes in your model and their corresponding effect sizes. It's glorious. P-core is a routine in Stata that for any slope that is directly in your model, it will spit out the R and R square versions of both semi-partial and partial. But it only works for slopes that are in your model. If you want to do effect sizes for linear combinations or multiple sets of slopes, we got to do those separately. There's also a test command that I will introduce you to, and there's an example online of NestReg that will do joint f-tests for sets of slopes as well. And the same thing happens in R. There's a package I found called ppcore. I'll try not to make a juvenile joke about that. Apparently pcore was taken by something else, is my guess here. So you've seen that as well already. That also works for only slopes that are directly in the model. For linear combinations or sets, you got to work with it. And then GLHT or ANOVA will also do this. And I found another one that does effect sizes and f-tests for part of it, and I'll show you that as well. So here's the process that my code followed to be able to do this. And this is why I'm so happy to have a way to automate it. The idea is that for something like this problem here, if I want to generate a semi-partial eta square as an effect size for, say, education, that would require asking for it as a set of these three slopes, beta 5, 6, and 7. So if that were what I need to do, then step one would be get the model sums of squares for the model that has everything, get the residual sums of squares from the model that has everything, and then get the total. Then I fit a nested model without the slopes I care about. So I would take the three education slopes out of the model and see how much the sums of squares were reduced. So then I end up with something called effect, which is what you started with minus the reduced model version. So essentially, what was the contribution of education and those three slopes to the sums of squares? That's what we're trying to isolate in the full model. Then with these ingredients, you can compute your semi-partial eta square, how much of the R square is that set of slopes responsible for, or your partial version, how much of what could have been explained that wasn't already explained did those slopes explain? And you're like, am I going to write that in a results section? Exactly my point. Add a total is a lot easier. And then you get to repeat these steps for as many different permutations as you need effect sizes. However, I'm also taking pity on you, and your next homework 5 over this example will use sequential models, because that is still probably the more common thing people do in practice. So it'll be like, add a predictor, say what happens. Now keep that predictor, add another one, see how much R squared changed. Add another set of predictors, see how much R squared changed. So it's a little bit more straightforward in that case. A little bit. All right. I don't know if I want to do this yet. How about I stop and ask, how are we feeling? We're not feeling good, are we? See, I knew that, and it's totally fine. This stuff gives me a headache. What's the big picture? Let's look at the beach while we answer that question. What's the big picture? What are we talking about?
Like complex family.
What?
Complex family.
Complex families? Yes. We're talking about what happens when you put multiple predictors in the same model and they got to fight each other. They're fighting each other for dominance in turf and rooms. And if the predictors have stuff in common, we got to somehow address that common stuff. By the way, this is the motivation for experimental designs in which you have manipulated people to like multiple conditions. Like if I say I'm going to manipulate I'm going to assign people to group A or B in this dimension, and then I'm going to go within A and assign people to either 1 or 2, and within B within 1 or 2, you are creating two predictors that are uncorrelated. And you will have the best chance of each of them having an effect because of that. When you can't manipulate and randomly assign, your predictors are measured. They're going to be related to each other. So like as a real world example, let's see, trying to think of one, in one of your homeworks, I used to do a lot of collaboration, with Mabel Rice at the University of Kansas. We just, paper I'm working on right now. She has a research area of specific language impairment in children. Have we talked about this in this class? Maybe? Okay. I talked about it at some point from this chair. That much I'm certain of. To whom, I don't know. Children with specific language impairment are not developmentally delayed. They don't have any issues except for whatever reason they're just bad at understanding grammar. Like they just have this very specific language debt. The intelligence and other developmental abilities are all fine. So this is like a special population. And in addressing how these children process language and the difficulties that they have, every reviewer 3 is going to insist that you control for mother's education before you say anything about the rest of the story. Because apparently it is my fault if my kid has a problem. Now, what about father's education? Or what about grandparent education? Or is education necessarily the defining factor of everything? No. But this is a convention in that field. So every model I've ever ran for her had mother's education in it, like because someone was going to insist that it's there. So then the question is, after I control for the obviously related stuff like that, what are the unique effects of having this condition versus not? Or being a child whose parents read to you more frequently versus not? Or being a twin. Actually, this is more common in twins for whatever reason. Can you think of any other research areas where you have to control for something or no one's going to listen to you? Medicine? What would you have to control for?
You have to have a control group to compare that like has a condition versus the group that doesn't have a condition, say if you're trying to develop something that's.
Yeah, so controlling for previous diagnoses or something like that. I used to do also work in cognitive aging, and you had to control for chronological age before anyone would talk to you. Because then the question is, what is the role of health or activity or physical function beyond just how old you are? Because how old you are is uninteresting. Now, it turns out aging is not bad for you. Getting sick is bad for you. So don't do that. That'd be my recommendation. But every field has these things. And so, like, these are real-life research questions of how do I characterize what diagnosis brings to the table after controlling for your demographic information or your income level or all these other things that aren't malleable. So that's the big picture. It's like we have multiple predictors, they're fighting against each other. How do we talk about what each brings to the table and also what they all as a set do to work together? Okay, does that make it this much better? No? Okay, fine. I tried. Do I get credit for trying?
Yes.
Okay. And this is the first time you've heard these words, right? So we'll go over it, and eventually it'll sink in a little bit. But I like semi-partial eta square as how much of the r squared did your predictor get? The end. And I like partial r's because they match the interpretation of the p-value. What does this predictor uniquely bring to the table, and how much is that? And d is the same thing as partial r if it's in standardized mean difference instead. And I will show you how to get all these numbers, okay? Easily, more easily. Stata users, it's not quite as easy, but it's better than it was before. All right, any questions before we wrap it up for the day? Now, we hung in there, though. Everyone's awake. No one's crying. It's wonderful.
No smile.
I cried earlier. Okay, so Thursday back on Zoom. I will see you then. Let me know if you need anything homework due tomorrow.
Okay, very good.
Bye
Thank
for
you.
now. Bye, Zoomers. And I will, yeah, I'll hang out for a few minutes after class if